Alright, y'all. This here's video 14-2. Colligative properties, vapor pressure lowering, freezing point depression, boiling point elevation, osmotic pressure, and some calculations. So, first thing we look at today, what are colligative properties? Hey, colligative properties. These are properties that will change, but they depend on the concentration of the solute particles and not necessarily what their identity is going to be. It's pretty much just how much you put in. Okay, so what are some things that are going to be colligative properties? Okay, the first one is vapor pressure lowering. So vapor pressure will be affected by a solute. Okay, and how much it gets changed by depends on how much you put into the solution. Okay, so if you add a non-volatile solute, non-volatile means has low vapor pressure, so it won't evaporate. Okay, when you add it to the solvent, it lowers the vapor pressure of the resulting solution. Okay, so what happens? Okay, you know water evaporates, so as it moves upward, it causes a vapor pressure. Okay, and some of it also condenses back in. Okay, now, according to the book, what they say is that adding a solute decreases the concentration of the molecules at the surface. So because there's less molecules, there's less to evaporate, so there's going to be less vapor. Okay, but that's not true because remember, going back to previous sections, okay, previous chapters, this solute molecule right here cannot be at the very surface. It has to be surrounded by water molecules. So you can never really ever get solute at the very surface. The top layer of every single solvent must be solvent. Okay? Solute cannot be up there. So that reasoning doesn't really work because you cannot have solute at the surface. Okay, so what's the real reason? It's simply because the solute increases the intermolecular attraction forces, so it's harder for it to evaporate. Okay, freezing point depression. When you add a solute to a solution, to a solvent, the solution's freezing point depresses, meaning it gets lowered. Okay, adding a solute basically requires more energy to remove to freeze the liquid, which means you have to take out more energy, which means the temperature gets lower. Okay, so the freezing point will be lower than normal. Don't forget, freezing point. This is also the same as the melting point. Okay, so what happens when you throw salt onto ice? Okay, it basically, ice needs to have a temperature of 0 degrees Celsius. If the temperature is colder than that, it won't melt. But if you can drop the temperature below 0 degrees Celsius, okay, so let's say you drop it down to -2 degrees Celsius, and the outside temperature is 0 degrees Celsius. Okay, now the ice will melt. Okay, boiling point elevation. Okay, because you lowered the vapor pressure, more heat has to be applied to the solution to make the vapor pressure equal the atmospheric pressure. Okay, so normally, let's say the liquid has a vapor pressure right here, atmospheric pressure is up here. Okay, so you have to add this much heat to make it boil. But when you make a solution, the vapor pressure drops down to here. So now, okay, the vapor pressure with the solute in it. Okay, now you have to raise it up more, which means you have to add additional heat. Okay, so the boiling point gets higher than normal. So salt water, as you found out in the little activity that you guys did, boils at a higher temperature than just normal water. Okay, osmosis. You guys learned about this in biology. Okay, if you have a semi-permeable membrane and it separates two solutions with different concentrations, okay, the solvent, the water, will move from lower concentration to higher concentration. Remember this. Basically, it's trying to equal out the concentrations. So in order to do that, it has to dilute the more concentrated solution. That's why the solvent moves towards the higher side. Okay, so here we got a little diagram. Okay, you have a tube with a semi-permeable membrane right here. Okay, and since this side has solute in it, this has a higher concentration, the water moves through and tries to dilute this side. Okay, now because this side does not have any solute, okay, it's continuously going to want to move because it will never ever ever get down to the same concentration as on the side with the pure water. Okay, so why doesn't all the water move all the way over? Because eventually this column gets lower, this column gets higher, and then you have gravity pulling down on the water. Okay, so the osmotic pressure is the external pressure needed to stop osmosis. Okay, eventually, force of gravity going this way and the force of water going this way, trying to push through, become equal, and the osmosis stops. Okay, so that pressure is called the osmotic pressure, and this pressure depends on how much solute you have on this side. The more solute you have, the more the water wants to come through, so the more pressure you need to stop the water from coming through. Okay, it's proportional to the concentration of the solute. Okay, now your second part of the activity that you guys were supposed to find a quantitative relationship between the boiling point and the concentration of solute that you put in. Okay, so how do you find, what is the mathematical equation to find boiling point elevation and for freezing point depression too? Okay, if you have 1 mole of solute in 1 kilogram of water, 1 mole in 1 kilogram. Okay, note what kind of unit is that? And this is kilogram of water, which is your solvent, not solution. Okay, so what kind of unit is that? Okay, well, what happens if you put 1 mole in 1 kilogram of water? The boiling point increases by 0.51 degrees Celsius. Okay, this is not the boiling point, this is the increase. Okay, and the freezing point will be lowered by 1.86 degrees Celsius. Again, this is not the freezing point. Okay, so boiling point would be the normal boiling point, which is 100 degrees, plus the 0.51 degrees Celsius. Okay, so that means this solution should boil at 100.51 degrees Celsius. Okay, the freezing point drops from the original temperature, so which was 0 degrees Celsius. It's going to drop by 1.86 degrees Celsius. So that means your freezing point is negative 1.86 degrees Celsius. Okay, now, what if you don't have 1 mole in 1 kilogram? Well, what was this supposed to be? That is the molality. Okay, so how do we find changes in temperatures? This right here, the triangle, means change. Okay, that's a Greek symbol delta. Delta means change. Okay, it doesn't mean heat in this case. When you see it in front of something, it always means the change. So the change in the freezing point is equal to Kf times m times I. Okay, Kf is known as the molar freezing point constant, and this depends on what the solute is. Oops, sorry, not what the solute is. It depends on what the solvent is. So as long as you use water as a solvent, Kf will always be the same. Okay, delta Tb, this is for boiling point. Okay, Kb times m times I. This is the molar boiling point constant and also depends on the solvent. Okay, m is molality, okay, like what we just talked about before. Now, what is this right here? What's I? Okay, the Kb and Kf values depend on the solvent. You can find them in the book. So if you change the solvent from water to alcohol or something else like that, you need to look up what the Kf and Kb values would be. Okay, so what is I? I is the number of moles produced from 1 mole of dissolved solute. Okay, meaning, suppose you took something like sodium chloride, dump it into water, it breaks up into Na plus and Cl minus. So 1 mole produces 1 mole and 1 mole. So I would be the total number of moles of particles you get, which would be 2. Okay, if you did something like calcium chloride, CaCl2, that breaks up into Ca2 plus and Cl minus, but when you balance it, you need 2. Okay, so I here, you got one of these, 2 of those, I would be equal to 3 for calcium chloride. Okay, so if your solute is a non-volatile molecular solute and it's a non-electrolyte, I will be equal to 1. Okay, because what happens? 1 mole gives you 1 mole of particles. Okay, and for any ionic solute, I is always greater than 1. Okay, because you have to break up into at least 2 ions. Okay, now, little problem. Okay, what if I said go find the molar mass of a solute, and I don't tell you what the substance is? Okay, well, you can use a boiling point elevation problem or freezing point depression problem and figure out the molar mass. Okay, how do you do this? Okay, if the mass of a non-electrolyte solid, so right away that tells you, since it's a non-electrolyte solid, I must be equal to 1. Okay, and the mass of the solvent are given to you. You can find the boiling point, use the boiling point elevation or freezing point depression to calculate the molar mass of the solid. Okay, how do we do this? Well, here's a problem. You have an unknown solid, 3.50 grams of it. It's in 555 grams of water, and it drops the freezing point to negative 2.35 degrees Celsius. So what's the molar mass of the solid? Okay, well, first, use the delta TF equation. Delta TF equals Kf times M times I, and solve for M. Okay, you know I is equal to 1 because it's told you right there, right? If it's a non-electrolyte. Okay, delta TF must be the change in the freezing point, which is 2.35 degrees Celsius. It dropped by that amount. Okay, and Kf, you know, for water, look it up, 1.86 degrees Celsius over molality. Okay, plug it in, solve for M. Okay, once you solve for M, you know M, the molality, is equal to moles of solute over kilograms of solvent. Your solvent is 555 grams, which must be equal to 0.555 kilograms. Oops. Okay, so solve for moles in this equation. Once you solve for moles, the mass is given to you right here of your solute. That's 3.50 grams, and then you're going to divide by the moles that you just found from this problem up here. Okay, so you'll have a problem like this on your review worksheet, and a problem like this on the test. Okay, so here's your review question.